Our next presenter will be Dragos Horvath, who's coming to us as a long-time user of ChemAxon. And he's currently working at the CNRS in Strasbourg. And he obtained his PhD in Lille and then worked in a couple of academic positions, and then was head of molecular modeling at CEREP. And today he will talk to us about molecular descriptors.
So it's my pleasure to be here back again after having missed it out last year. I'll just briefly mention the last developments. We are now, it's not completed yet, so it's still a work in progress. It's about property labeled fragment descriptors, and first question is why? Well, because everybody knows fragment descriptors. I mean, they're really a golden standard, and they come under various shapes and forms, starting from fingerprints and hashed fingerprints to actual fragment counts, such as the ISIDA sequence descriptors, where the idea is fairly simple. The user specifies the minimum, the maximum size of the sequence. The computer breaks the molecule down, says, well, this is a sequence. I will monitor the atoms contained in there. I could, is the laser gun? This one, okay. So I have oxygen, carbon, carbon. Oh, it's this one, nitrogen here, and the star means an aromatic bond. The dash is a simple bond. It's present once. We have a, if you get the other branch, then you have a nitrogen here, so you see the principle. They're very nice because they're open-ended, they're comprehensive, and they're intuitive. I mean, every chemist understands what we're doing there. It's not the Rundich index, it's not the Balaban index, and not black boxes like topological indexes. They are very good at capturing scaffold-oriented informations, but I mean, say atom symbols are not informative of the actual chemical context, isn't it? Here we have N, but what kind of N? It's an amide N. Nobody tells us this. Well, not actually true, because you could infer this an amide N by looking at other sequences. I didn't count all of them, but the actual context information is dispersed between different fragments. The other problem is that they don't really care for ionization status and other more subtle things. Now, a little bit in the red corner of the boxing ring, you have an opposite approach, which is fuzzy descriptors, such as fuzzy Pharmacophore Triplets, where the idea is to look at feature triplets in the molecules and to fuzzily match them against a set of basis triplets and then count a similarity-weighted population level for each of these descriptors and build the fingerprint as an integer, a vector of integers or even of reals if you dare to. They're nice because they really account for the physico-chemical nature of the functional group. They were made to be pH sensitive. This was a topic of another ChemAxon presentation a couple of years ago. And they're fuzzy, so they're well suited for scaffold hopping. The problem is that they have a fixed format. So if you count triplets, then you don't count pairs and you don't count other multiplets, whereas with the fragments, you were basically looking at the things that were in the molecule, not at a predefined set of fragments. So the idea is straightforward. Why should we marry them? Combine the best of the two worlds. So use the open-ended enumeration of sequences and branched fragments. We call this Augmented Atoms. But we can use context-dependent labeling. Pharmacophore type, charge-based topological potential, log P contributions. This is something that's not done yet. And we can introduce the pH dependence if we do this. And you'll see how we come to a population-weighted fingerprint. There's a fuzziness in there by the use of wildcard atoms. I'll come back to this. So there's probably no, it's not a revolution in science. Other people have thought of this idea as well. There might be some originality, nevertheless, in the way in which we construct the descriptors. And it's actually a two-step approach. The first step is typing. The second step is fragmenting. Typing is done by using the ChemAxon API. So you take a molecule, push it to the standardizer, push it to the pKa plugin, and take each microspecies populated above 1%, call the P-mapper and get its pharmacophore types, call the P-mapper with a different set of typing rules, we can get force field types, and call the charge plugin, get the Gasteiger charges. If the charge plugin crashes, then set the take resonance structures to false and try again. This gives us the electrostatic potential flagging. So for each microspecies, we can generate these population values and the flag strings as a new property field of the molecule, and then we loop over all the microspecies and we export the annotated molecule. And well, pharmacophore types are the one you'd expect to. Aromatic, hydrophobic, acceptor, donor, negative, positive. This force field typing is based on CVFF. And then an annotated SD file will look like this. After the structure, you got population 1 is 95%, pharmacophore types in population 1. You notice that some atoms can carry multiple types. This is an acceptor and a donor at the same time. Force field types, electrostatic potential types, I'll tell you a little bit more about those. So topological electrostatic potential is just Gasteiger charge divided by topological distance plus some self-term where we say that the own field distance is a 0.4 topological distances, just in order to avoid the division by 0. And with respect to the potential an atom I feels, we can classify it on strongly negative, negative, neutral, positive, and very positive, using this kind of overlapped fuzzy mapping. So up to there, it's very negative. In between, we cannot decide, so it's both very negative and negative. It has a double flagging, then it's negative. Well, you got the idea. So this is the electrostatic potential typing. And now comes the fragmentation. So for each molecule, here we have 2 populated microspecies. What do? We look at microspecies 1. We get the sequence, but this time it's labeled by property. Pharmacophore flag in this case. You have a multiple property in one atom. Well, again, lower upper sizes are user-defined. And this sequence will produce 2 fragments, both with an acceptor and a donor. And the fragments will be counted at plus 95, equaling to the population size. This other guy, which has an aromatic / acceptor, will produce 4, populates 4 fragments in my descriptor space. And the other microspecies, which has here an anion, a negative, will come with its own contributions, but those will count only plus 5 because of the lower population level. And the sum of all these terms will then be the molecular fingerprint. Okay, there's certain options. One of them is the bond information toggle. If you set it on, then you monitor the bond types as well. If you set it off, it will be just plain sequence without distinguishing single bonds from aromatic bonds from double bonds and so on. The wildcard atoms are used in order to ignore the actual type of certain atoms if necessary. So the strict typing is the one we saw. But if we turn wildcards on, then these the sequencing will produce the strict match, of course, and then it will allow each atom in the sequence to count as a joker, and each pair of atoms will be replaced by jokers and so on and so forth. Except for the terminal atoms, everything can be replaced by a joker. And this case is actually, if you look at this descriptor, well, this is something which already exists in ChemAxon in a slightly different way. This is just a topological pharmacophore pair. It tells you how many acceptors you have, how many acceptor-donor pairs separated by 5 bonds do you have in your molecule. So pharmacophore pairs are just a subset of our descriptors, just a peculiar case, and so on. And then, of course, the game goes on. So this is the special remark for the pair counts. Now, augmented atoms are, as I said, branched fragments which are centered on an atom, and it includes successive coordination spheres, a little bit like in pipeline pilot circular fingerprints, but it accounts for the topology, so for the bonds, so the nature of the bonds as well. In this case, you would say this is a donor. Its first shell includes an aromatic and a hydrophobe, which aromatic is bound to 2 other aromatics, and which hydrophobe is bound to an hydrophobe and an acceptor. And because this has a double type, you will have two augmented atoms matching this fragment. Without bonding, then you'll get the same, but a little bit more condensed. The wildcards may operate as well, so you can replace these intermediate atoms. And if you replace everything but the central and the terminal atoms by wildcards, then we call this a tree descriptor. So the sequences, the pairs, augmented atoms, and the trees are the extremes in terms of fuzziness. So just to wrap up, okay, so we use the different atom typing schemes. They are derived for each microspecies, and then the fingerprint includes population level information thanks to the ChemAxon API. So we got sequences, augmented atoms, with or without jokers, and sequence from sequence to fuzzy wildcard sequence to topological pair, or from the augmented atoms to the fuzzy branch fragments to the trees. Nice. So what? Well, we did several tests. One is neighborhood behavior monitoring, so checking whether the similarity principle holds in these descriptor spaces. So are similar molecules displaying similar properties? And we looked at a set of experimental screening against 5 proteases. So you take each active for each one of these, and you calculate some obscure local ascertained optimality, which you don't want to know how it is done. So the bigger this psi value, the better is the neighborhood behavior. And of course, neighborhood behavior not only depends on the descriptors, it also depends on the metrics according to which you calculate the similarity. So for each active, the local optimality score depends on the used descriptors combined to the used metric. So how can we know whether descriptors are good or not? So this is a little bit So these are the benchmark descriptors. You can read this by looking, so pair, electrostatic potential, and these are the size limits between 2 and 8. Sequence means sequence. Symbol these are colored by atom symbol, just as a baseline to check how well atom symbols fare. pH is pharmacophore, and then you have the sometimes you have the B flag and W flag. So you can see they are of varying dimensions. This means the number of fragments that was populated based on the 2,500 considered molecules. And these were benchmarked against some more classical descriptors, the Gisbert-Schneider's CATs, ChemAxon PF, the Pharmacophore Triplets, 3D Pharmacophore descriptors, liquids by Gisbert-Schneider, and some privileged descriptors. So this is a subspace of relevant descriptors that were important for describing tryptase activity. Tryptase is one of the 5 targets. And the deep red is the actually predicted tryptase QSAR score. Dissimilarity metrics, I'll go quickly through these. There's nothing new here. And the scoring scheme is actually a Formula 1 race. Why? Because there's the same problem. We have, if a descriptor is a car, then the metric used for neighborhood behavior is the driver. The final score is obtained by the pair of the two, so we don't know whether if neighborhood behavior fails, we don't know whether the descriptors were not good or whether the metric wasn't good. So these are the local optimal score. An active molecule can be considered a race. So we look at the average scored for one descriptor D1 with the different metrics obtained, and it's a biased average. And then we look who's doing the best average optimality, and we rank these descriptors. So for molecule 1, D1 did the best, followed by D2. Well, you see the idea. And then they get points. The winner gets 6 points, the winner gets 10, the second gets 6, and so on. So then you have for each descriptor ranking, and it should give us some idea. Now, look at the chymotrypsin. There were 12 actives, that is 12 races. This championship lets the Augmented Atoms based on symbols win. They had 4 gold medals, 2 silver, and so on. This is the number of points. How nice. Actually, if you look at the winners list, all of them are dominated by symbol annotated fingerprints. That's a bad idea. Why did we work so hard to color them otherwise? Well, you can understand, because by chance all the actives here have this trimethyl group, and it's specific for the actives, and none of the other coloring scheme can evidence the trimethyl group. It doesn't stand out neither in terms of pharmacophore nor in terms of charge. So it's only the SI here that gives it specificity. So this is a bit of biased contest. Factor 10A. Much bigger championship. There's 81 races there. Well dominated by the tryptase-specific privileged descriptors, because F10A is quite correlated in terms of responses with tryptase. Trypsin, only 3 actives, but the winners are completely different. They're pharmacophore-driven. Tryptase, well, that's a no-brainer. This was fitted for tryptase, so it obviously works well with tryptase. Then we got some symbols, we got some electrostatic potential. Urokinase plus minogen activator, again. So I don't see any pattern in these tables. It would be scientifically much more rewarding if there were one, but I don't see it. The only thing that can be said is that if you look at the overall ranking, so these are the ranks, the given descriptors obtained in each, for each target. You could see that these three descriptors are more or less homogeneous in their performance. So this guy makes a second place, and in the worst case, it's 18th, so it's never ridiculous. This privilege space, which seems to do very well for some targets, then completely loses the game for the fifth. So if you look at the average rank and the rank variance, three descriptors appear to be not the best, but the most reliable, the ones that convey less surprising, less chaotic results. And we also did some QSAR. So we fitted some log-P models. These are validation, so these are real robust QSARs. We're not talking about the typical 20-molecule-based model that is unfortunately so often seen in literature. We're talking about 10,000 compounds. And surprise, surprise, log-P, shouldn't it be dominated by polarity, by the charge-colored? Well, the charge-colored, they're a real disaster. Symbol works well, pharmacophore works well. Charge, no way. Then we made a HERG model. It's a categorical model, so it says active, inactive, and we validated it on PubChem molecules, again, a notoriously difficult set. We got some models with balanced accuracies above random. Other models are random, and guess which? Well, the electrostatic potential again. I have to admit these calculations are not finished, so there are some QSAR still going on. So, time to get to the conclusions. Pharmacophore-Colored Tree descriptors seem to be the most versatile ones. They did well in neighborhood behavior against other colored fragments, but also against other descriptors, pharmacophore descriptors. They also did very well in the QSAR studies. In the neighborhood behavior tests and in QSAR, other symbols and pharmacophore-colored fragments were reasonably steady as well. But electrostatic potentials, they failed in QSARs, but were quite useful in neighborhood behavior. Now, why is that? One possible explanation is that their dimension is much higher. It happens that you say, well, how comes you only have 5 electrostatic potential types, but you have 6 pharmacophore types? Yes, but it doesn't mean that all the combination of the 6 pharmacophore types are equally populated. You'll never see a donor sequence in a normal drug. These sequences will be dominated by the default hydrophobe part of the skeleton. Whereas with electrostatic potentials, a carbon which is close to a polar group will not be flagged as neutral. It will be either negative or positive. And there are many more possible combinations with the electrostatic flags. Another possible explanation is that after all, log-P and the hydrophobic effect is not a matter of charge, of polarity, but it's a matter of entropy, as studies tend to suggest. And I'm afraid I'm done now, because yeah, the rest is appendix, so I will definitely not go in there. Thank you. Do you have any questions?
Thank you very much, Dragos. Are there any questions?
Thank you. Just a quick question. If your fingerprints are very, very long and you're comparing your QSARs on fingerprints, can you comment on validation for overfitting with the data sets for having very long X variables, or a large number of X variables?
I didn't quite hear you.
So
Well.
If your fingerprints are very big,
Yeah.
and you're doing a QSAR based on a very long fingerprint, could you comment on the validation you did to avoid overfitting your data set based on very large X variables?
Yeah, well, the QSAR fitting was done by genetic algorithm on a quite large scale. So although the fingerprint size can be quite large, we limit first. We cannot seek for mine for models out of 40,000 possible descriptors. So this is first limited to 5,000. So there's an upper limit of cutoff in terms of descriptor size when we do QSAR, and then the genetic algorithm tries to pick the good combinations. It doesn't mean, of course, the equations typically contains. For log P, the average equation had about 30 terms. The fitting size, this fitting set being of 3,000 molecules, a ratio of 30 variables to 3,000 data points makes sense. And of course, you can learn models based on smaller data sets, but it's risky. The bigger the size, the descriptor, you're right, the more difficult it is to model small data sets.
Are there any other questions? Okay, well. Oh.
In the columns of the descriptor?
Occurrences of?
How many times they occur in the structure? So in your descriptor, did you use occurrences like in the ChemAxon Pharmacophore fingerprint?
Yes, yeah. Well, you use occurrences based on population percentages. So. You don't count, practically you count the occurrence of how many times this fragment is seen in 100 molecules, out of which the population of 100 molecules is divided, is split among the populated microspecies. So you have 95 times microspecies 1 and 5 times microspecies 2. So if a fragment is present once in the molecule and is microspecies independent, its population level will be plus 100. It's just a matter of scale. And if it's present only in the major microspecies, its population will be plus 95. But if it's seen twice, then its population level will be 190. Because it's seen twice in the species occurring at 95%. It's a trade-off between the two.